devoted to the 50 years of Lev Beklemishov, and I will talk about what they call residuated Kleene algebras or residuated Kleene lattices, or in a gist, structures where we have, a monoid, so we have algebraic structure with the multiplication operation, and also we introduced iteration, which intuitively should mean something like the unit, then A, and the union of all of them. So in order to talk about the union, we need to have lattice structure. So basically we need to have only unions, so this is what is called really Kleene algebra. But here we also introduced the intersection, which is a dual one. It is technical, and so this is just the difference in terms between. Yeah, no, I didn't say it about that. This is the new one. So I'm talking about the monoidal operation, the unit associated with them, the star, which is the main thing, which is the iteration, lattice operations, and the preorder, which is associated with the lattice, and these two will be residuals. So this is the monoid structure, and these are the residuals. So if you have a monoid which has a preorder, and the monoidal operation is required to be monotone with respect to the preorder, the unit is not required to be, say, the minimal or maximal element, just the unit, the monoidal unit.
But it's preserved.
It is preserved, yes. So, and then one can define the notion of residual or division by the following equalities. So it should be coordinated with multiplication, but in terms of the inequality. So usually in algebra we'll have equality there, but here we'll have the inequalities. And also because our structure is not required to be commutative, basically, there are two divisions, the left one and the right one. If such operations exist, they're unique. But their existence is not so sometimes you can have a preorder on a monoid, but which doesn't have residuals. So we consider the case where these residuals exist. And then we have the lattice structure, which is just taken from the less or equal, and we suppose that these guys always, for every A and B, they exist, they meet and they join. And this is the iteration, and for the iteration we have two possible ways of axiomatizing it. So the general situation is what they call just generic Kleene algebras, or in this case generic Kleene lattices, which in the presence of the residuals can be axiomatized in a symmetric way. So usually when you don't have the residuals, the axiomatization is a bit different, which you can, for example, see in works by Pratt or Cozen. You usually write something like that, that A, the unit is less or equal than A star, A is less or equal than A star, and then we will say something like A star is less or equal than A star, and A star A is less or equal than A star. And also for the, so it is defined as a fixed point, so the second one says that it is sort of a minimal one. So here also there will be AB less or equal than B and BA less or equal than B. And this is asymmetric, and when you don't have residuals, there are also notions of left Kleene algebras and right Kleene algebras, where you leave only one of these axioms. And there could exist Kleene algebras for which say the star is the left Kleene star but not the right one, or vice versa. So in the presence of the residuals, they get symmetrized. So they're equivalent, and this was shown by von Pratt in one of his papers. So the references are Pratt 1990 and Cozen 1994. The second possibility is to define the star not in this sort of inductive definition, which is the first one, but using the notion of star continuity. So just define it as really the supremum of these nth powers of the element. So the P and Q are here are technical, the context, in order to things work okay, in order to cooperate with the multiplication. If you put units instead of them, then you'll get just that. So the star continuous case is described as follows, and as one can notice that if you have star continuity, then you will have the first axiom also. So, but not the other way around. So, here we'll talk about what are the differences between the star continuous and the general case, both in a situation where we have residuals, which is the main topic for today, and what is the difference where we don't have residuals. So, standard examples, which are all star continuous, first is the algebra of languages over an alphabet. So if you have a formal language, you can consider iteration of the language, which is the cleaning star on formal languages. So you just take, if the word belongs to this iteration, if it can be split into several parts, each of which belongs to this language, but they can be different. Also the empty word is there, the empty word is allowed. And all other operations are also there. So it is a distributive lattice of real set-wise intersection and union, and it also has multiplication, and you can also define divisions. It's residuated after. And the second example is the algebra of binary relations, where there is composition. Also, you have set-wise operations, intersection and union. So you also get distributive lattice. So the unit is the diagonal relation, and iteration is a reflexive transitive closure. And also you can define residuals there. It's also residuated linear lattice, residuated action. So this is more close to the notion why they call it action. So the action is when you, in a relation, it's sort of a non-deterministic action. You start with an element and go to another one. So if it's a functional relation, it's going to be a deterministic action. Here is a non-deterministic action. You can consider some restrictions, like, for example, you can, in the second one, you can consider finite automata and some sort of accessibility relations, and that connects it to the first one, where instead of arbitrary languages, you can consider regular languages, or languages generated by automata. So this is a scary slide with the logical system. So it should be really scary because it is an infinitary one. So this slide depicts a calculus for which is a Ganson-style sequent calculus for the theory of star continuous action lattices, which is called act omega. So the omega rule, which makes this calculus infinitary, is here. So it has an accountable number of premises, which is needed to derive that A star is C. So you can easily see that this calculus basically corresponds to the axiomatization of the star continuous action lattices, and well, you can easily prove some trivial completeness theorem if you consider the class of all of them. Strong completeness theorems like completeness with respect to relational models or language models are yet unknown and possibly hard, open questions. So, but basically, if you have these guys like meet and join, they will be incomplete due to the fact that there is no distributivity derivable here. But if they're set-wise, you will have distributivity. But if you remove these operations, it's a good open question. So this calculus was, in this formulation, was given by Bushkovsky and Palka in a series of works at the beginning of the zeros. 2005, 2008. So 2008 was basically the final paper in Studia Logica where Bushkovsky gathered all the stuff. So what they proved, first they proved that they have cut elimination, they have some other syntactic properties, which is non-trivial, of course, because it is an infinitary system. So the proof here is a tree which has finite, it doesn't have infinite paths, but it can have infinite branching. And also the depth can be also unbounded. So you have for different branches, you can have different depth. So cut is eliminable, and the second result, which is interesting for us now, is complexity. So I will talk about this a bit later, about results by Bushkovsky and Palka. So I will talk about something a bit different. So I will talk about the calculus where we consider positive linear iteration instead of the usual one. So positive linear iteration is basically the same, but you don't allow the empty word, the unit. So you consider a semi-group instead of a monoid, so we don't like the unit. And here we also replace.
In which sense it's infinitely, so it's not finitely generated?
No, the calculus, yeah. The proofs are infinite.
Yeah, okay.
The proofs are infinite. So, and we'll show that this is inevitable. This is the goal. So, for the general case, we'll have the following axiomatization. So we just remove the unit, and for the star continuous case, you'll get this. The standard example is the algebra of formal languages, but without the empty word. And a variant of relational semantics also exists. But in the relational semantics for this situation, you will have to make things a bit trickier. So usually when you consider relations, they're arbitrary, just arbitrary relations. Here you need to consider subsets of a fixed relation. And this will give you a complete semantics for the Lambic calculus. So, also, we consider the multiplicative only fragments, so we don't have meet and join. So it's just divisions and this positive iteration, just to consider the minimal fragment for which I will prove the lower complexity bound. And this is actually an extension of the Lambic calculus as it was here. So this is also the Lambic calculus, but allowing empty left-hand sides. So you see this is a fusion of two things. First one is the theory of residuated monoids or residuated semigroups, which was actually axiomatized by Jim Lambic in 1958 and 1961. And second is the theory for, so there's actually three things. The second is lattice theory, and the third one is the theory for iteration. And since we have cut elimination, the system is absolutely modular. If you remove some operations, you just remove the corresponding rules. So this is the usual virtue of cut elimination, which we have for Jensen-style sequence calculation. So here we consider only two of them. We consider the Lambic part and the iteration. So the complexity result is that this theory is pi10 complete. So what is pi10? So sigma 10 is the set of all recursively enumerable, class of recursively enumerable sets. So it means that why sigma? Because what means recursively enumerable? It means that there exists a witness such that it witnesses the fact that the object belongs to the set, and the fact that it witnesses is decidable. So it is of the form something like exists x, or exists y, r of x, y. It is the same that x belongs to this our set. So for pi10 is dual. Instead of existential quantifier, here we have the universal. So the pi10 problems are exactly the problems of being in a complement of a sigma 10 set. So sigma 10 recursively enumerable problems are greater than, form a greater class than decidable problems. So there are undecidable recursively enumerable sets, which are classical results in theory algorithms. Therefore, there also exist pi10 problems that are not decidable. And if you have a pi10 complete problem, which is in a sense one of the hardest problems in the class, they're of course undecidable. So we'll get the fact that this calculus is undecidable, but also it is not recursively enumerable, because there is the thing called post theorem, which says that if a problem is recursively enumerable and co-recursively enumerable, then it is decidable. Because you try to enumerate positive solutions, you try to enumerate negative solutions, and since they together form the whole universe, one of these strategies will win, and this will be the decision algorithm. It could be vastly inefficient, but nevertheless it exists. So Poe's theorem says that the intersection of the classes of sigma 0, 1 and pi 0, 1 is the class of, precisely the class of decidable problems, which is called delta 0, 1, and therefore it's like, the picture is like that. So you will have delta 0, 1 in the center, decidable problems. So here we have sigma, and here you will have pi. And the hard problems are going to be here, and they could not belong to both sigma and pi classes. So therefore, even before I gist the proof, we can show that we have axiomatized, so we here and Bushkovsky and Palka in this situation have axiomatized our system using an infinitary calculus, so a calculus where the proofs are infinite. The complexity result shows that this is inevitable. So no, because if you have a finite proof system, which means that the proofs are finite objects, and you can verify the proof algorithmically, then it's always in sigma 0, 1, by definition. Because it's exactly of this form. What does it mean that an object is provable? It means that there exists a proof such that, and this R is a decidable relation. Therefore, if we have pi 1, 0 hardness, we don't have finite proof systems. So therefore, this is the best thing you can have here. So Bushkovsky and Palka proved pi 1, 0 completeness for this calculus. And the difference of what is stronger here is that we get rid of the meet and join. So we do it in the purely multiplicative case. So I think on this slide there is also a gist of proof. I will go quickly. So the idea was that they encode the totality of problem for the context-free languages. So there is a context-free grammar, and we ask a question whether it can generate all the words in the alphabet where it is defined. Well, this problem is known to be undecidable. And if you open up the undecidability proof, it's actually a proof of pi 1, 0 completeness, because it's an inverse. So the proof usually goes like that. So it says that for a Turing machine, you can generate, say, context-free grammar such that the Turing machine holds if and only if this grammar is not total. So this word which is not generated by the grammar is actually going to be the witness for the halting problem. So it is the proof of the undecidability goes through complement. Therefore, the original problem, halting problem, say, was sigma 1, 0 complete. Therefore, this one is pi 1, 0 complete. And the encoding there went along that they translated this context-free grammar into a lambic grammar. So for each letter, it associates lambic formulae, and then they used meets and joins in order to encode the totality. And in this proof, we used a not well-known result by Safiullin, one of the students of Marty Pentos, that every context-free grammar can be encoded as a lambic grammar with unique type assignment. So this is a bit a technical thing. I will not go into details, but the idea is that you can from the grammar you can construct. So this B2 should be just B. So the alphabet is just of 2 letters, and you construct actually 3 formulae, A, B, C, such that the sequence of A, B, and B, A, B is derivable into C, if and only if the word is in the language. So this is the sort of not well-known result about lambic categorical grammars, and this yields that you can check the following: A plus multiplied by B plus, and all of these under plus implies C is roughly equivalent to totality. It's not totality itself, because the word should start with A and end with B, but the problem of being able to generate all the words of this sort is also pi 1, 0 complete. Unfortunately, Safiullin's result relies on the fact that there is no empty word. So therefore, the question about the purely multiplicative fragment of the calculus for residuated cleaning lattices, not for positive iteration lattices, left as an open question. This open question was actually posed in the paper by Bushkovsky and Palka. Unfortunately, I don't have a complete answer now. So this is a modification, and it was used because Safiulin's result relies on that. But I hope that we can do it also for the cleaning star. So this was something about the star continuous side. So on the star continuous side, we have the calculus, which has a complicated derivability problem, which is not recursively enumerable. Therefore, we need infinitary methods. So on the other side, this is an axiomatization for generic case, not necessarily star continuous. So it was used by Pratt for the case with clean iteration. This is a modification for positive iteration. It's just taken from Pratt's paper. And here I usually make this remark, which I find quite funny actually, that Pratt in his paper in 1990 doesn't cite the paper of Lambeck. You can see that this calculus actually includes Lambeck calculus as a conservative fragment, and Lambeck 58 is 40 years before that. But nevertheless, Pratt seems not to be aware of that. But nevertheless, he cites Girard on the paper of linear logic and says that accurately this is something, a variant of linear logic. So, I usually make this remark not in order to say accuse Pratt of not knowing about Lambeck or ignoring his work, but from my point of view, this means that this is something really interesting because people really come to this notion from different points of view. So these residuals, which are sometimes called Lambeck operations, and so these divisions actually are interesting to other research schools from different points of view, which I find a bit of inspiring because it's something natural. So I think Cozen started citing Lambeck at some point, but nevertheless, it's the first paper of Pratt which does not cite it. I checked that. So this is an axiomatization. Unfortunately, it is not a Gensen-style sequent calculus with cut elimination and all this stuff. And this is one of, I think, the most interesting problem in this field. To give a good, in a sense, so analytic axiomatization for the generic case, the not star continuous case. So as we can see that the big calculus is pi10 complete. So in the case where we have the star, it is done only by Bushkovsky and Palka for the big system where we have meet and join. For the case with positive iteration, as you can see now, we have even a more fine-grained result for the multiplicative only fragment. But nevertheless, it's pi10 complete. The calculus of Pratt is, of course, sigma 10. We don't know the lower bound, but the upper bound is sigma 10. What can we do? Therefore, first, there exists an action lattice which is not star continuous. Because otherwise, because the theories do not coincide. Therefore, there is some algebraic object which is a counter model. And the equational theories, or we can say inequational theories, do not coincide. They differ. And for positive iteration, even in the fragment without meet and join. So, and this is the difference from the non-residual case. Because in the case where we don't have residuals, but we have join, and I think also meet. As shown by Dexter Cozen, the equational theories coincide. And therefore, this, a fragment of this system will actually serve for star continuous case also. And there will be no such high complexity. But nevertheless, the first one, they are different. So there are not star continuous Kleene algebras, but nevertheless the theories coincide. So this is the non-residual case. For the residual case, this is. So an open question is to construct a concrete example of formula that separates it. Possibly also not that easy because we have a non-constructive proof, that we have complexity-wise proof. The second question is low complexity bound for not star continuous case. So the first one, for an action lattice which is not star continuous, also we have proved it non-constructively. there is an example which is really a modification of Cosen's construction for the division case, which is which shows that there exists an artificial example of a lattice, which is an action lattice, but this is not a star continuous one. I will maybe skip the details. So it is a linear order of specific form, so it is a minimal maximal element in the middle. There is some pairs of numbers which are ordered lexicographically. It is commutative in the sense of multiplication. The star is defined trivially, and you can see that it is really a Kleene star in the sense of the first definition, but it is not star continuous because, for example, if you have 0, 1 to the power of n, it just doesn't have any supremum, because on the second you will have 1 and then the integers. So you will have, say, 0, 1, 0, 2, etc. But here you will have z. So they will not converge to anything. But the star, as declared in this model, is just the top element, which is just a very, very maximal one. And it obeys the inductive rules in this example. So in Cosen, instead of z, there was natural numbers. I added z here. So this example is mine, but I didn't find such an example in literature, for example, in Pratt's or Bushkovsky's papers. Maybe they did this, but didn't show. So I used z instead of n because we needed to handle for division. And division is basically because multiplication is plus, division is going to be minus. And therefore, you needed z. But this seems to work. So, and you can also take a positive iteration algebra from here just by placing a plus just a multiplied by a star. So it will be a semigroup. Well, every monoid is a semigroup, and the positive iteration is just defined like that. So therefore, this is an example of a non-star continuous action lattice. But the other question, that the equational theories, they do not coincide due to complexity reasons, but is there a concrete difference? Well, it is an open. Also we introduce another system with non-well-founded derivations, which is a variant of the Amiga system. Here we have finite branching, but we can have infinite paths, infinite branches. There is a correctness condition, which says that on every infinite branch you have to unfold, really apply this rule infinitely many times, because otherwise you can just have malformed deadlock proofs where you have you just do the same several times and do it as cut with itself. For example, cut with an axiom. So this is an incorrect derivation example. So here it is even the rule is applied infinitely many times, but the traces do not match. So this guy actually goes here, and here you instantiate in u pi plus, and this is going to prove something incorrect, because pi plus implies p is not a correct principle in Kleene algebra. And they're equivalent, but in the presence of cut. So cut elimination here is work in progress. There is a notion of what they call continuous cut elimination, which is used for non-well-founded proofs. It's basically a co-inductive method. When you push your cut upwards and upwards, so in the finite case, also finite depth case, the cut will just disappear on top of the axioms. Here it won't, but then you go continuously. You say that all the proofs, maybe with cuts, they form a metric space, and then you just push the cuts upwards, and then you go to the limit, and the limit proof, so you prove that this metric space is complete, so there is a limit, and in the limit proof there is no cut, because it's shown that there is no cut on level 1, no cut on level 2, and all these simultaneously give the proof. So Savateyev and Shamkhanov did them in their works for Gödel-Loeb probability logic and for Grzegorczyk logic. So they had these systems for model logics. Here it also should work, but I just didn't have enough time to do this. So for circular proofs. So returning to these works by Savateyev and Shamkhanov, in that they calculated, they were based on classical logic, and therefore the sequence were just sets of formulae. There was contraction rule. And when you apply these rules, they, of course, enjoy subformula property because they are normal, say, Genser style sequent calculus, and cut there was eliminable. Therefore, on every infinite path, there could be only actually a finite number of different sequences. And that means that when you go upstairs, you prove, and due to pigeonhole, at some point you will have the same two formulae. So the formula will repeat. And after that, you can stop developing your proof and just say, look, I have already seen this formula, and then I can just propagate my proof regularly, just copying the same argument. Which I think it's a good, maybe actually a scandalic thing to say in philosophical institute, because it's basically proof by sort of intimidation. So what is going on in a circular proof? I start proving a formula, then at some point I get it at a formula A. So here is A. Then I go upstairs, I find A itself, and then I say, well, hey guys, we have already seen A. I already said that, therefore it's true. So the proof looks very, very strange. So I started from proving A, then I proved A from itself, and say that A is true. What? It's strange. But the correctness condition makes everything okay, because on this step I actually unfolded the inductive definition, and therefore it's actually just induction. So when we prove something by induction, we also apply the same statement, but for a lower, say, parameter. So here just the parameter is hidden in this proof system. So these two formulae look graphically equal. But nevertheless, the parameter is somewhere inside, because each time you unfold the plus, you actually add another A. So this is the notion of...
So it's induction or...
Yes, it's basically, here it is induction of on the number of this. So A plus is something like the union of all A to the power of n. So it's the induction on n. So here in this omega system, you have this rule. So how to prove that A plus implies something? You need to prove that for any n, an implies this. So, and you actually do it by induction on n. Here, the base case is this one, and this is the inductive. So, informally it is what is happening. But formally speaking, in a circular proof, you will have this graphically the same formula, which looks strange, but it's just syntactic sugar, it's nothing. So again, for the systems which were considered by Shamkhanov and later Yuri Savatev in their works, for Grzegorczyk and for Gödel, for systems based on classical logic, this was sufficient. So since the total number of possible sequence was subsequence built of subformula of the goal sequence was finite, therefore each proof was, as they said, regular. It could be transformed into a circular proof. So here, the system with circular proofs is weaker than the system with infinite proofs. Why? Well, due to complexity reasons. Because the system with circular proofs is an example of finite, say, proof system. So it is at least recursively enumerable. The existence of a circular proof is a finite witness for provability. And the system with omega proofs was pi10 complete. Therefore, they do not coincide. And now we have this interesting situation. So we had the big system with omega proofs or non-well-founded proofs that were equivalent, and they correspond to the star continuous case. And then we had Pratt's calculus, which is sort of non-sequential calculus, and we had this calculus, which is the circular subsystem of, so also with finite proofs of the non-well-founded system. And the natural conjecture was that they actually generate the same. And this is actually true. So the circular, here is an example of a circular proof. Here is another example. So this system is unfortunately asymmetric. So here we can do this only to the left, not to the right. It is due to some technical reasons. So if you have an asymmetric system, it corresponds to Pratt's axiomatization. If the system is made symmetrical, is potentially more powerful, but I don't know the correct answer. So therefore, if you want to prove this one is proved easily, this one is proved a bit harder, but nevertheless, the theorem is that if you have this circular system, then it is equivalent to Pratt's axiomatization. So we have a nice property that we have non-well-founded proofs that capture the star continuous case, equivalent to the omega calculus. So the circular proof system is unfortunately weaker, but this is inevitable because just due to complexity reasons. But it also corresponds to an interesting class of algebraic objects, namely the generic residuated action lattices, or action algebras. So unfortunately, the circular system has to be equipped with cut in order to obtain this equivalence. And this is another open question, maybe a cut-free system. So the problem is when you have a circular system, then cut elimination becomes a problem. So if the circular system is equivalent to the non-well-founded one, then the cut can be propagated in the non-well-founded system and removed, and then you again wrap up your big infinite proof into a circular one. But here this is impossible, and if you try to eliminate the cut from a circular proof, the proof stops being circular sometimes. So, if you want to move your cut inside the cycle, just run along the cycle and never stop. So this is another open question. So I will go quick enough. So there is the standard language interpretation, and the open question is whether it is complete. We have already seen this on the slides. There's a partial result by Nadia Ryzhkov from 2013, where the plus is in a very restrictive position. So they have completeness for the omega calculus. Nevertheless, the inequation of the formal language semantics is also pi10 hard, because this encoding also works there. But we have the lower bound, we don't know about the upper bound, because we don't have any completeness result, we don't have any calculus that corresponds to it. So in the full language, with the where we have the unit and meet and join, we know that completeness fails. There's no completeness result. But nevertheless, by Bushkovsky, we have a pi10 lower bound by the same argument. So it is potentially a different logic, but it has still pi10 lower bound, and upper bound is an open question. There are partial results by Bushkovsky. It's also an interesting question how to handle distributivity and this stuff, and even without iteration. It is an open problem as in the Lambert calculus. And the same is for relational semantics. So for relational semantics, again, if we have meet and join, then we have incompleteness, because distributivity of meet and join, which is true if they are setwise, it is not derivable. It is the standard problem of linear logic that distributivity is not derivable, therefore additives. Nevertheless, we have pi10. So this, formally, the first one is a new result, but it is actually an adaptation of the method by Bushkovsky. So I think I will skip this due to lack of time. It is even more completeness, and thanks for
about exponentials.
you want to just look at the exponential.
It's like bank in linear logic, yeah? Linear exponential, yeah?
Yeah, so once you ask this question, I will have the indulgence to show this last slide and talk a bit about that. So here we include the bank or exponential connective taken from linear logic, but in the non-commutative situation. And using the bank, you can encode the derivations from theories. So actually, bank allows something like deduction theorem, which is we don't have basically the deduction theorem in linear logic, because what is the deduction theorem? If you derive something from a set of axioms, it means that you can use them many times, or actually refuse to use them, because an axiom is something that you can, an extra axiom or a hypothesis, you can use it freely in your derivation. So linear logic doesn't allow that, because it is relevant and it is linear, it's affine. So you cannot use something twice, and you cannot refuse to use something. You have to use all your resources. Therefore, in pure linear logic, like the Lambic calculus, for example, you cannot do any sort of that. So you have to put the needed number of copies. But if you have this operation that allows for structural rules, you can see that this guy allows all possible structural rules. Weakening, exchanges, and contraction. Then it restores deduction theorem. So you can, inside derivations of pure sequence, you can encode deriving from sets of hypotheses, finite sets of hypotheses. So if you have only the Lambic calculus, and we're at the bank, then we get undecidability because we can encode derivations in type 0 grammars in semi-truth systems, which are undecidable due to classical results of Markov post. If you have bank and star, then you can encode Horn theories of linear algebra, which are pi11 complete by a result by Dexter-Cozen from 2002. So therefore, if we have the exponential and the star, we have vast growth of complexity. So the exponential itself is sigma 1, 0, and it's also the upper bound because it's a finite calculus. The star itself is pi 1, 0. Well, not that small, but also something quite. Well, this is pi 1, 1, which is much bigger. So, by the way, the question is whether it is the exact bound. Maybe it is harder. Because here, this Horn derivation, they are pi 1, 0, pi 1, 1 complete. So Dexter-Cozen shows both upper and lower bounds. But with this bank, you can also do some more nested combinations. You can do bank, inside you can also use the star, inside you also use banks, and also Lambic connectives, maybe meet and join if you have them. So potentially it could be even bigger than pi 1, 1. So my personal conjecture, it should be pi 1, 1, but it's unknown, so it's an open question. Another answer to your question, maybe more technical, is that here, yes, we have the full powerful bank, which is the real linear logic exponential. Actually, encodings of this style are available if you have what they call a sub-exponential, so a bank which allows only some of the rules. So, for example, you usually don't need weakening. Actually, it can be modeled using the units, so it's just something technical. And also, a more fine-grained thing, you can remove exchange, but then you have to use the non-local version of contraction. So, non-local version of contraction means that here you contract only neighbor formulae. In the non-local version, you can contract formulae that have a distance between them. So in the presence of exchange, it doesn't matter, but if you don't have exchange, you have a non-local contraction. And actually, I claim that, and we claim it in a recent joint work with Andrei Shchedrov, Vivek Nigam, and Max Kanovich, that I think Sergei Artemov knew this ages before, but published, that if there is no exchange, then the correct form of contraction is a non-local one. Because if we have only the local contraction and nothing else, we fail for cut elimination and also some stuff like that. Okay, so this is about the bank. Thank you for the question, because I had the opportunity to.
But maybe if you can just couple also like applications, just make some connections.
Yeah, it is a good question. So кого-то выключи. So the first application I started thinking about this with is the application in linguistics. So, well, it could sound funny because we have pi 1, 0 completeness here, but nevertheless, for example, if we have a sequence of words which are coordinated in a sense, something and something and something and something and something, and or even better, A, B, C, D, and E, for example. This is an example of the iteration in language. So if you have, say, a noun phrase, then N with the star is something like a finite sequence of noun phrases. So what to do here? We need to have a very, so these results suggest that we need to have a very restricted fragment of our calculus to use in categorical grammars and linguistics to get a tractable and decidable systems. So, and people really use them. So if you see, so the Lambic calculus is used for building natural language analyzers, and in these systems they even fight for polynomiality. And sometimes it is even possible. And but they also include a very, very weak version of the Kleene star. Basically, they just remove the omega rule, and this means that they can derive assumptions of this type, but not vice versa. So the only way to derive A star implies something is actually this. So it derives itself. But yeah, but stuff like this, which is also easy facts, even in their systems, even this is not derivable, but apparently they don't need that. So this is an interesting thing where you can consider more say, logical fragments. For example, apply star only to variables or only in specific polarity or something like that. So this is the linguistic application. The other one, what they call action logic, is maybe even more plausible for people in computer science, that if you consider these
думаю, он все равно слушает.
So I just repeat because for the people from overseas who are watching us now. One of the applications of the iteration could be the sense of common knowledge, where we have many agents. They have joint knowledge. I know, say, all others know. But then we can say that I want to know that you know, and you know that I know that you know that. And this is the iteration of knowledge. So this is not, of course, this framework is different. So there is model logics with reflexive transitive closure, which is a K star K plus and stuff like that, but this is closely related to this. So the iterated process on knowledge and or belief or modality in general. And I think they also encounter some problems like that. But I don't know, by the way, for Q+, maybe the cyclic proofs coincide with the generic ones. So I think Daniel told me something about that. He wanted to do this for PDL, but started for the, I just don't remember it for now, but I think at some point they tried to do some research on circular proofs for K+, and arrive at a finite axiomatization. Well, not finite, but the circular one, so with finite proofs. And here, the interesting thing for me is that it is, well, if you consider, say, first order theory is like arithmetic, then of course any inductive system is weak. It is incomplete, just due to Gödel. So therefore it's not amazing. But here it is a purely propositional system, but nevertheless it is, say, pi 1 0, even pi 1 1 complete. So big complexity going out basically from nothing, and the circular system starts its own life without its, big brother, which is the infinite system, and its analysis becomes a more tricky and interesting problem.
Okay, thank you. Okay, now we have something to discuss more. Or we may think is that our next speaker is absent, so now Volodya Vasyukov will come 15:30. Well, actually it's in an hour. So yeah, back for lunch. Yeah, for lunch we may go downstairs.
So you have a
Huh?
You have a
Yes.
We will just go and continue the discussion there.
Let's do this. Or maybe I can tell the drawing. The question. Huh?
There were people listening right now.
No,
It's
basically it's recorded everything. That's useful. Then they may edit it a bit, just cut that.
And will it be published on the web page of the institute?
Yes. So it will be available. Video.
Yeah, it's great.
It's simply a YouTube channel.
My YouTube channel.
So you make stream and it gets recorded.
Let's have somebody come in, kind of like,
Yeah.
I didn't know about this.
Well, actually, Martin Andrews told me on that. So we published a preprint with three authors on the course of big name sub-exponentials and non-commutative linear logic. So we did complexity, sigma 1 0 equals without this iteration. We did cut elimination accurately, and we did this notice that if we have only low contraction of elimination effect. So, and when I showed this to, actually, this latter part was really something that should have been done by people before us, and we did a sort of search in the literature, we didn't find it. So Vivek said that some French guys should have done that, but we didn't find it. Then when I final version will make some.
Тут можно так вот, если и там спускаешься в двор вот этой высотки. Там есть такой тайм, там через дюбку. Да. Прямо вот отсюда налево, там стоянка, это прям иди.
Так, Сергей, знаю, как торговый центр, на самом деле.
Причем вот прямо налево, до тупика, там церковь слева, ты ее проходишь, и там ты найдешь, программиста еще может пустить прямо под двор. Там вот как ты будешь спускаться, там напротив арка. То есть ты выйдешь прямо на набережную, пройдешь через двор, внутри. И вот как ты выходишь из этой арки, слева сразу. Ну, кстати, вот сейчас на декорама открывается. И там стоит поставь приложение на себя.
Хотя вот я могу уложиться.
At that point they started searching for some functional systems.
А то мне как-то тоже влом.
Покажи, что делать.
Much better they found this ladder company, which you like it better because they were
Это надо на двор.
easy to understand. But
немножко разговаривать.
But at that point they also discussed the systems with banks. They understood all. Похож на but they didn't. So this is. But what is the paper which we gave them?
Ну, может, знаешь,
School of logic. So they did some. So this is that linear logic in its cycling system. There was basically that's intuition, and Ludwig calculus is intuitionist. Because it's only one. Nevertheless, it's really clear. And this is very strange that an intuitionistic system should be as much weaker. But the trick is that the language of the Ludwig calculus is exactly carved in the way that it doesn't allow any formula that's distinguished classical intuition. So they don't have negation. So we cannot have double negation or A or not A. For A or not A, they don't have disjunction. So, and this disjunction is used here, not sufficient for A or not A. Well, of course, people know some formula like Pierce formula or something like that. But for Pierce formula, you actually, when you derive it, you also need, I think, wiggling at some point.
Знаешь, он еще
Also, if you have an exponential that when it's wiggling, it appears in some polarity. So that's really the Ludwig calculus is intuitionistic. But basically, the language is so weak, and the structure is so weak that you actually, now I think that you don't allow to say that Ludwig calculus is intuitionistic, because this language is no different between intuitionism and classics. But you have bank, and it is full of the bank and the question mark. But then you have it. And there is also intuitionistic technology, which is also includes the language of this thing was noticed by so this technically this looks more say yeah, and also we don't have the force, which makes sense. So this was the Skelet's. Which is Skelet's example was community who made it not. So this is this is now we presented this part of this work at a workshop which was in honor of city and now they gathered at for volume, which are one Tennessee or something like that, but there's always within volumes very good time. So, well, it's always so, Andrei Shidov always warned us against journeys such volumes. So, but that was the good thing because it was a
So he didn't say anything. Possibly he considered that because I had a talk with him while I was in university, and he said that, well, they first had some problems with the real management because this was a special issue, but the new regulations require that one of the editors of the special issue should be members of the editorial board of Hong Kong. So they managed to find such a guy, but this took some time, and then this, of course, crashed the schedule of himself. Management time to think about that. So, and after that, I didn't hear about it. So, I sort of think it's not very good to write about it now, because we did it all the time. Paper, but now it is still not because of the issue. But maybe not, maybe so. You said interesting.
Yeah.
But I think they could consider that because while they did all these negotiations with Elsevier, it was only formal discussion, so they didn't really talk about concrete items. So they just talked about how this volume would be organized, and therefore only after they established the membership of the editors and all these businesses, then they will start assigning reviewers and soliciting the papers. So therefore, you have to be able to. Yeah, the problem for you would be if you have sent to your manager.
No, I mean, in a way it's not so bad.
Yeah, that's okay. So, I knew that they could accomplish it. So, for us, I think the only problem is that this time is longer than our grant period. Sometimes we have grants which are say that 3 years. So, and you are not allowed to, so if you report for your grant, it has to be, yes, so first you cannot, it is meaningless to report a paper after the grant. Because you already got all your money and you but on that hand, they do not allow us to use papers that were submitted before the grant started, which is also logical because how can you support a paper by a grant you can do it before you want it. Right. And therefore, if the grant is shorter than the journal lag, then you cannot use it. And therefore, people now prefer these fast publications like conference proceedings, which are also saying this was concentrated they fear just before conference. So this one is the shorter trick. So well, I can maybe could ask him now because I don't know what is the status. So I met him, I think it was a spread. So I was in with underwriting semester and I need to understand the relation to the States. So you go now to Cuba, to there. So I met him and asked him
погоди, да. Там 3 попытки, и она блокируется. Окей.
Блин, я постоянно забываю.
Не, французская клавиатура.
На зерте, что ли? Вот
А?
это? На зерте это дурацкое, что ли? Ну там не кверти, а на зерте.
Да, это называется.
Ну там были первые буквы просто. Вот, все. На зерте. Вот, кверти, а там на зерте.
Да. И плюс цифры. Там шутовые.
Ну, это уже...
Не, у меня заняло несколько лет, вообще, привык, ну, я там торчал 10 лет.
Да это я помню тоже. У меня своя-то была русская, а там
Да.
публичный компьютер. Там был.
Ну, да. А потом уже где-то и привык, и уже не хочу.
в смысле, со звуком, там, ну, и там это тоже нормально, да, поэтому нет.
Давай, тут закрыть не забудь.
Да, хорошо.
Давай. But the place itself, actually, I mean,
Indiana.
yeah. Yeah, campus is nice.
But the rest is not.
The rest is not. You need the car.
Yeah, fair enough. I think that's the problem with a lot of American universities. Hearings. I think they like land grant universities. No, they're
Well, actually, in Russia, it was also the case. It was somewhere close. Yes, there is a bit more of a public hospital. Right.
Well, Russia does not seem to have the antipathy towards public transport which the United States. There are some big cities in the States that have public transport because the city can function without it, but outside of the city,
Look at Russia, the same, I mean, if you go even some distance from Moscow, yeah, there are some buses, but, yeah,
my son decided that 4 a.m. was the time to get up. My son decided it was 5 a.m. was the time to get up this morning.
But maybe he goes to bed.
Oh, yes, he goes to bed at 6.
Well, I will go sleep more. So.
Only after big jet lags. Once I came to the States, I think there's stuff for watching hours, scriptures, like that.
And my twin daughters, they unfortunately have the opposite. So one tends to get very late, then sleep, and the other one gets early.
Out
and
of the
gets up.
market.
Maybe 2 different rooms.
I don't have to do.
I was sort of an outlet person in the day. Tended to get up late and go to bed late. But when I was a student in the US, where the schedule is different, so they have the seminars in the daytime, and in the evening is usually I I absolutely switched. So I woke up at 7 and at 8 a.m. also to my office. So
Is there a reason for this, the late seminars? I mean, the major of the States is like starting at 6 o'clock.
that should be crazy. I think the reason is that people work in people have different affiliations, right?
Yeah.
And the seminar, they want to gather people from different universities, mainly. So it's not convenient for a person to come to a seminar in the daytime because you kind of teach.
But the thing is,
So you finish at 2 o'clock?
It's not always dependent on you. So but this is the tradition. I think that, well, I personally now I don't like to go about really, even, especially if you have a long community.
but I remember in Junior, there were also even seminars.
There were. I never went to a seminar of the sisters. The latest was
Like
for
the seminars?
the suicide seminar.
But there was a later one, something like Kusev, and that was the same, because then many people came who would go.
That's true. That wasn't an official thing. That was
Yeah.
Absolutely.
So they had their own.
Yeah, pretty sure you could do it.
But no, I was sure the
Something was
But it's also related to the fact that sound is like,
people
life everywhere, and that becomes
think it's also
became a means of Israel, and it was supposed to start at 6 maybe or 7,
yeah.
but it never started before 8 or 8:30.
No, it's very crazy. So it's okay to live near the university. So when you sort of end your day with the 7, so you go to the 7 and then say at 9 a.m. it stops, and say 9:30 already at home, and that's something at 10. But if it takes people to commute, for me it takes to commute on a half hour basically home. So some people have to pay the pump home business or in the suburb of Moscow, so it takes even more.
Yeah, this is what
Yeah, but for you, I think your location is quite nice. So
it's okay. It still takes a solid hour.
yeah. Unfortunately, the other gate is not near the metro station. So the Moscow State campus is adjacent to the metro station, but the main building is in the center of the campus. And Steklov is actually not near the metro station. And actually, even
Some coffee, I mean, sorry.
I think even somewhere it takes me 1 hour to go to work and go there, but the top of the issue basically.
Yeah, that's what the.
Thank you. No, спасибо.
But so you have some evening classes?
No, this is when I was a student. This is when I discovered that there was something. I was in this course and I was taking notes. And I remember being on the top of the page.
So they added a new course. Oh, sorry.
Yeah. Yeah, usually. Because I know a story that one of his students, so he's kind of asked her to prove that Ptolemy astronomy was false and actually written some, I don't know. Yeah. Just by comparing data, her data with kind of modern data. And she did it, and I know like firsthand, my brother. And so she compared it with modern data, and she not only proved that standard chronology, but she also noticed, and that was the latest she published, I think important result, she noticed difference about 300 years between, data that Ptolemy's used from earlier observation and those which he did himself, which is not explicit in here, but she somehow identified all the data. This data, yeah, completely proved standard, but he actually kind of didn't allow her to, couldn't get the diploma and so on. It was really bad.
What would she do? Like, would she just change?
No, basically that was, she was some kind of mathematical physics. So that was not really, so she was pushed to do this historical thing, right? But I hope she's fine. I don't know. But he's a good teacher. I don't want to learn it. He's also very good in drawing. He just explains things and he draws geometrical things, and that's really good.
However, when has been on the great order, but I think there is, for example, proof that homotopy group of so-called isomorphic to Z. Well, I think that false proof is more simple than the classical proof with fundamental cover. In my taste.
Sorry. So that guy introduced this stuff called practical force. All students in computational geometry. The first year when they go into a specialization. And people from other departments complain why all the students have to study geometry and computers instead of something else. And there were new practical courses invented, but the development logic was not that fast. So some years our students took the algebraic course, which was in Sage, counting some things in finite groups. That they were not very good. But our specifically algebraic. And then there was an initiative to do final logic. And so we should talk. We'll teach some complicated students.
We have on our department similar course called group search, but it's implemented already by Vladimir Smirnov in the end of the 90s. He works on those. So, and deduction. And students need to install a virtual machine to emulate those. I want to talk with Martin to change that course for color.
But isn't this software open source?
Yeah, open source, and moreover, there is a possibility to give home exercises, something like that. But kind of natural deduction.
Classical propositional logic.
Well, that's a very, very boring. Well, we don't want.
You don't get any deductive immediately. This is interactive. Well, classical proof switch is theoretical.
Yeah, but that was the beginning.
No, confusion is including. And by the way, it would require a very minor modification. We just replace some of the rules.
Yeah. Rule system for classical propositional calculus implemented for DOS. I think that sounds great.
It's really a proof system.
Yeah, kind of proof system.
No, I believe it's not that. I thought it was something like a pizza. You know, there's something like this. I think it was and sort of passed away. And they developed a proof system for, but it wasn't really classical, so we didn't write ideas like it was specifically designed for set theory and set theory with experiments.
I think that's similar to Isabel and Islam.
Yeah, but that was old, and it also had this problem that it ran out of some outdated architectures and stuff like that, and Andre was quite an old guy, and he just continued developing stuff, revision and stuff, and make the problem. And maybe not, I mean, even those, they had some parts maybe you don't see. So, really remember screens like that where they had some formal style interfaces and ran out of some things like those. But I thought that in your case it was something like that it was really a strong and interesting system, but just old written and well, so it's like saying in banks they still have code in COBOL or something like that. So, because they just, the policies of, say, banking were written in its own language and were, say, confirmed by the top management of the banks, and you cannot just place it because then the verification procedure becomes a question. And at that point, they actually, there was no formal verification of that, but their workaway was that they just came that very close to the management and made them approve specifications to go itself. So the policies are written here, they are just like that, and the dispute becomes the law. It's okay, so you don't need to verify the code against itself.
There is something, if you update your law too often, then there's it's like it ceases to be the law.
Totally.
Because the law works with some.
Yeah, but even in programming there is this thing called reference implementation. So sometimes they even define some programming language for reference implementation. So we don't say that there is a gold standard, they say that, okay, we produce an implementation and say, well, this is the definition of the language. So the language I speak is the correct language.
Well, that is it's actually related to the matter this morning that we already maybe, that sort of thing to confuse things that happen. But there is simple idea that kind of civilization began with writing. Right? And what was specific to writing that it allowed to transfer knowledge, whatever, from one generation to another. Right? And that was progress even over just language. And now with computer, we are more closer to just culture without writing, because it is more or less like chasing. We update, we do something, next time we do next, and there is little trace, and there is not this idea that we keep, not there is bad kind of, but still there is kind of danger that, not next generation will just look up to the ridiculous what we have done today, And that basically means that we become to live without history in kind of prehistorical, which is nothing special actually. They're not very bad. Everything is except that. Not for maybe invent something. No, I actually hope that kind of technology. It's actually part of, I don't know, idea that, for example, something like material proof, well, at least with historical things, right? Why all these scriptures or something are important? Because it's the best evidence of, how to say, origin of historical truth, of course. And can be only material, right? Material. And even if it's, I don't know, some documents, it's important to have original, because then you may analyze and careful on that.
Yeah,
But that's really evidence.
but there is another, maybe not the opposite, but another idea or another approach to that topic. The people that are strongly support linguistic evidence. So analyzing the texts rather than analyzing the our methods are basically precise. So they're helping. And some people, like for example, in the books of studies now, where he analyzes this poem of verse. So there is no physical idiom, but how do you know? Yeah, so therefore, how do you know whether they were original or not? And it was a big debate in Russia.
Yeah, but actually this fermenter stuff you say.
Yes. Fermenter doesn't even bother about physical. So he can include all this in his conspirology. So, for example, there was the fermenting was really funny because it's not like the door. Yeah. So Donald positioned himself as a humorist. So he has all the rights to do it. It's okay. Fomenko positioned himself aside. So it's a different thing. But so with Fomenko there were problems like this. He said that all these artifacts were forged. So first he said that the manuscript was forged. Then they gave him some stone inscriptions and stuff like that. And he said that they were also forged by these bad guys who wanted to falsificate history. And then they found some rocks, I think in Iceland, with something written which corresponds to the standard history, but not from because one he also had some idea that they were also.
Well, I think it more looks like kind of trolling.
Yeah, but no, it was also a business project. It's really business, so I think it's Nosovsky who really made business from that. Because the older books of Fomenko, they were not that, say, scandalous, they were not that. So they looked more sciencey. So he analyzed some texts, he analyzed some artifacts, he analyzed some astronomical things. And
So actually I looked at such stuff. He just does not understand how, he understands how proof works in mathematics, but not.
yes, no, he was
That's history.
Yes, he was wrong, but at least it was not sort of, say, things that managed to work. So he just wrote wrong papers. It's his own. But now he writes, say, books for the general public in order to actually make money. So if you come to a bookstore, then you will see your shelves and shelves of these fancy printed books. People really like that.
I've read some parts of his books. Well, I think Fomenko needs to study relevant logic. So there is a lot of confusion, kind of, for example, if, I don't know, 2 + 2 = 4, then Alexander the Great was Russian. So I think it's kind of irrelevant.
Yeah. No, there's no problem. The problem with self-consistency there. There are many problems.
Yeah.
So no, this is the idea. So it's okay that your theory, say, contradicts other theories. It's even okay if it contradicts facts, because we can say that they are facts. But if it contradicts itself, it's really crazy. So, and also, by the way, Znanie was one of the guys who actually attacked from the linguistic point of view, and he was really good at that. Because when it doesn't know linguistics, and linguistics is really a very precise science. you need to understand. And the funny thing was that Zalizniak, just as sort of a joke, suggested also some flamenco style exercises, like he said that Perm and Parker were the same, and Sambias and Vilis. But the funny thing that some of these things appeared in newer book by Flamenco. So he really understood that as good ideas to develop his theory. Venice and Venice, yeah. So Venice is a town in Ukraine. And he said that it sounds like Venice, but actually it's the same city, and so the same for Parkman Fair. And this means that all this Italian Renaissance and all these great stuff which was the culture of Italy actually happened in former Soviet Union, Ukraine, and so this was, but this was not from America originally. It was Zalizniak who just wanted to make fun of his style of argumentation. But afterwards, yes, so Zalizniak said that if you use the same, the argument similar to what Fomenko uses in his books, you can easily get the following, say, proofs, which is obviously false. But nevertheless, Fomenko used, maybe even these examples, I think, some of them came to his new books. She's thought to be a very good idea. So, and I think the other difference from the old thing is that now Fomenko is much quasi-patriotic. So in the old books, he just attacked the official history, tried to find what he understood as flaws, but they were mainly not about, say, trying to prove that everything was invented by Russians. And there were also on some things which are not that obviously true in commonly shared history, like the history of ancient Egypt, for example. So the dating there, I think it is even in official studies, it is something problematic. It's not that we have the unique and absolutely known true history of these pharaohs.
I've already seen this book called Jesus Christ was born in Crimea. And Madonna too.
But what Zalizniak said about, there was also an argument about this law of religion, which was the one part, and it is serious, not everything. Because we don't have artifacts. They were all lost. So,
But what we do have?
no, we have the text.
Which form?
No, we have the text which was printed under the rule of Catherine II. So this was this problem, that it was copied, and it's say semi-known that before the war with Napoleon we had the original text, and this text was lost during the fight.
Original text was in
Lala was So, but Muslim didn't show it also to the general public, so there are not many evidence that this text really is. And also, of course, this was also a copy which was made also in the medieval times, but later than that.
Well, it's a more common situation. We don't have the plate or origin.
So, but therefore, but the question is whether this text is really original, or whether it was written by someone else. And because the problem with this text is that it is quite a unique example in Russian literature. So it's not the standard saying, the standard line. And there were many people who did serious or less serious attempts to attack this conjecture and claim that it was written by some person of the 18th or 19th century. And Zalizniak, you know, there's a book which you quite into people. It's actually a collection of articles against each of these attempts. So the earlier attempts were quite naive. So they said that, for example, Pushkin himself, which was Christian, well, he was not a linguist, not an artist, so just a noble man who collected ancient things, and that he would just for fun do. Zalizniak said that no, because for forging the text in ancient Russian of that epoch, this guy has to have very good knowledge of statistics, which was not available at that point to
why he explained just, I think it's interesting for you, how he became a mathematician, because first attempt was history. And so he made some student historical paper about...
Well, by the way, it's not just a paper, it is a famous study of the ownership of land in the medieval Novgorod Republic. So it's, by the way, it's published, and I didn't read it, but historians say that it is quite a good study for, it was not even a student, he was a school child. Because before he talked about what he joined the university already as a mathematician.
Yeah.
He studied as a mathematician, but when he was a school child, he attended the seminar by one, historical seminar, and started his historical studies. And at that point he published, well not, he didn't publish it, he prepared a paper and a talk for this seminar, where he advocated some...
But he gave, his words were, no, I didn't give myself, that I proved, I provided a proof for
something.
And then when I was told that it's okay, but one proof is not sufficient. And then he said I would
Go to that.
single this so that one proof is
That's too
enough.
He joined the medical department, became a prominent mathematician. So really brilliant. And the post-history of that was also this work. So it was given as a talk at the seminar, and Markushin, despite his criticism that he said that there should be several groups, he said that the work is nice, especially for a school teacher. And people thought that it just was a normal talk and nothing was good. But nevertheless, after Gogorov's death, I don't remember who, maybe it was Sherenin who analyzed his postmortem. And so he just took kind of the paper in his home and started saying, categorized it and publishing, and they found some, I think, a manuscript of sort of transcript of his talk. And this was passed to historians and published in a collection of articles and so on. And even in it was late 80s, right? And even at that time it was the novel literature. So it was really a good historical study, even from a professional modern point of view, because it was even before the war or something like that. So, but now it is published and one can read it. Yeah, so whether this is a famous thing or that, wow, I want to go here is field, one group is sufficient. Just how it's so hard to find several groups and maybe they'll do different things. But yeah, so by the way, the other proof, the funny thing that the other proof could not be found at that point because the other source of information on Novgorod history was not discovered. So there is in the northern areas, there was
Ну я тогда не пойду ничего видеть. А, не имею в виду,
information you could get from ancient times because the descriptions of the what are situation. So this was widely used, I think, in all say Islamic countries for writing some small letters, and which was not supposed to be as important to, let's say, Spanish paper. But only in the northern soils it is they could get say survive.
А я как раз выступал примерно во время пары. Чуть-чуть. До часа где-то.
Ну, я не понял, зачем я же на лекции.
Ну да, я Костя свалился.
Да, что с ним такое?
Отравился чем-то.
Питаться надо в разумных местах.
Да. Ну, Костя, да, мне страсть от шума. До добра не доводит.
Нормально, он не правда.
Ну, вот сын ошибок трудно. С шумом в частности.
Так, ну что, я не буду выступать, да? Все выступили, да?
Ну, я знаю.
So this is something fresh information which you can get even not to so it's funny to read that because the details are influenced by specific, not even for a historical period, but for a complete business case, which you could not analyze because we don't have English text. So we really don't understand semantically what is going on. We can only understand what the language they use, the style they wrote in. Some of the documents were destroyed intentionally by their own because they possibly contained some commercial. After they were used, they were used. But it was quite good find. The birch tree has some oil inside it. So like today, we will use paper or something like that.
Тут розетки раз через раз работают.
Не хочется рассказать.
Тогда придется проектор переключать.
Я просто переключу, да.
Ну, главное, чтобы там это гнезда нормально было. Так, и лучше вот этим микрофоном пользоваться, который ближе к вам, потому что этот фонит. Причем фонит достаточно...
Включишься? Нет, подожди, не, они зачем? Не, Володя, они просили, а ты можешь?
Не могу, потому что у меня программа другая.
Подожди.
Почему?
Так они записывают.
Да.
А что вы, подожди, а какой другой?
Я поставил здесь этот, как его, новый для этого, Word поставил, и тут презентацию поставил для макоса. Там такие эффекты специфические, которые на стандартном высоких.
А вы можете,
Если я не буду.
а вы PDF не сможете сгенерить?
Нет, не смогу. Ну, хочешь, я принесу свой проект?
Нет, дело не в проекте, они просто, видишь, это на YouTube записывают через Excel.
Ну, не будем, потому что я не могу, я специально привел. Ты чего это дело, да, не согласен?
Ну, хорошо, да. Ладно, тогда я сейчас скажу ей. Ну, пусть звук запишут все равно.
Потому что это, все презентации, там же у вас анимация всякая, да?
Ну, конечно.
Ну,
Мы что частично видели мою анимацию.
да.
Она идет только в этой системе. К сожалению. Что-то она еще сразу экран несколько забочила. Хорошо.
Это можно подвинуть.
Нет, у меня здесь даже экран. Ну ладно, какой будет, такой будет. Черт с ним. Не укради счастья, конечно. запас, видите?
Я вас, так сказать, вечерней сессии, ну да, потом пойти.
Я еще там в университете.
Ага.
Ну, пораньше появиться, что может, сидеть доклад.
Микрофон этот, да? Какой-то, это что-то фонит, какой-то не фонит.
Что-то он у нас фонил.
Это нормально.
Вот это?
Это нормально, я его от себя.
Оно все равно все равно может. Да мне где-то чуть-чуть. Вот слышно, да? О, отлично. Супер.
Хочешь, можешь вот это включить?
Да.
Сейчас я тебе. А?
Вручную. А ну попробуй. Будет он
Подожди.
брать. Ну, может, и не будет брать. Кто его знает?
А, нет. Ну как?
Красивый тебе это, да?
На левой стороне.
Да ладно, давай буду вручную.
Да.
То время потеряю.
Ну давай.
Дома крутил вручную, тем более здесь режим этот хороший, знаешь. Сейчас я покажу, я имею в виду вот этот режим. Режим докладчика. Режим докладчика это для меня хороший. Поэтому мне так удобно будет. Окей. Ну что?
Окей.
Let's start.
We have our weekly session.
Yes.
Of this institute.
Okay.
Talk about behavior.
If reality is contextuality, does non-classicality matter? Yes, the topic is very complex because concerning the paraconsistent logics, exactly the Da Costa logical system C1. Nevertheless, I'll try to say something. First, abstracts. You can read this motivation for our use. Motivation for our use the term behavioral. Images from the computer science. The data should naturally be split into two categories: visible data, which can be directly accessed, and hidden data that can only be accessed indirectly by analyzing the meaning output of programs with visible output, called experiments. Since one cannot access the hidden data, it is not possible to reason directly about the equality of two hidden values. Two values are said to be behaviorally equivalent if they cannot be distinguished by the set of available experiments. The characteristic example is the behavioral algebraization of the paraconsistent logic C1 of Da Costa. Since C1 can be seen as an extension of CPL by a classical propositional logic by a paraconsistent negation, then the key data will be to leave paraconsistent negation out of the chosen subsignature while still including the classical negation. But there are also known the case of the so-called Da Costa algebras proposed by Da Costa himself for C1 together with the behavioral semantic. The question arises, what is the genuine context for C1, behavioral or another one? Trying to answer this question, it was to pay attention to such an obstacle that Da Costa algebra serves also as the foundations of paraconsistent set theory. Maybe such non-classicality is the source of confusion. Okay, let's start. First outline, we will speak first of the data types, not so much behavioral algebras, behavioral algebraization of the paraconsistent logic C1 of Da Costa algebras, and finally, non-classicality of Da Costa algebras. Okay, the motivation for use the term behavioral image from the computer science, namely from the algebraic approach to the specification and verification of complex, namely object-oriented systems, where abstract data types and object classes are defined by the properties of their associated operations. Algebras are considered as abstract machines where the programs are to be run. Such systems constitute a challenge for traditional algebraic methods, since they very often provide mechanisms for encapsulate internal data in order to make the updating of programs easier and the internal data protected. Consequently, the data should naturally be split into two categories: visible data, which can be directly accessed, and hidden data that can only be accessed indirectly by analyzing the meaning output of programs, with visible output called experiments. The role of experiments is to access the relevant information encapsulated in a state. Since one cannot access the hidden data, it is not possible. Since one cannot access the hidden data, it is not possible to reason directly about the equality of two hidden values. Hence, the equational logic needs to be replaced by behavioral equational logic, sometimes called hidden equational logic, based on the notion of behavioral equivalence. Two values are said to behavioral equivalent if they cannot be distinguished by the set of available experiments. This restriction induces the notion of gamma behavioral equivalence, where gamma is a subset of the set of original operations. It can be shown that the gamma behavioral equivalence is the largest gamma congruence, whose visible part is the identity relation. The possibility of having a restricted set of experiments also accommodates the existence of non-congruent operation. This feature of behavioral logic play a fundamental role, since it allows to cope also with non-truth functionality. Non-truth functional logics belongs to those logics, algebrizable or not, that can be seen as extending some given algebrizable logic by some new rules and some new connectives that do not satisfy the congruences properly with respect to the equivalence of the initial algebrizable fragment. Since behavioral equivalence is an equivalence relation that is only required to be compatible with respect to the operations in a given subsignature or the original signature. The characteristic example is the behavioral algebraization of the paraconsistent logic C1 of da Costa. It was proved by Chris Mortensen and later by Lewin, Mackenberg, and Schwarzer that C1 is not algebrizable according to the standard notion. The class of algebras standardly associated with C1 is not very interesting. The only true congruence compatible with the set of theorem of C1 is the trivial congruence, as proved by Mortensen. Therefore, no work has been devoted to this class of algebras in the literature. Let us introduce the logic C1 as a pair. C1, a pair of signature and the consequence operator. The single-sorted signature of C1, sigma C1, is such that it's simply the set of subs and the set of operations. Set of operations includes constants, TF, unary operation negation, and binary operation conjunction, disjunction, implication, and is empty otherwise. We can define an unary derived connective over this connective negation over this signature, such that this negation could be defined as defined with this definition where phi 0 is just an abbreviation of not phi and not phi. This is the right connective intended to correspond to classical negation. The fact that we can define classical negation within C1 is indeed an essential feature of its behavioral algebraization. The consequence relation of C1 can be defined in a Hilbert-style way from the following axioms. You see the list is big enough, but it's not so original. You see the left side is very standard, the right side concerns this operation, it is zero index, zero upper index.
So this consequent relation is not like, it is not semantic.
It could be defined from this Hilbert-style axioms. Simply there is not direct definition. And the rule of inference, using this rule of inference, we can define this consequence operator. It's only this, because there is no direct definition of this consequence operator. But it's standard way of definition. Also, it is defined as a logic weaker than classical propositional logic. It happens that the defined connective, this new negation, indeed corresponds to classical negation. Therefore, the fragment with this waveline and other standard operation corresponds to classical propositional logic. So, despite of its innocent aspect, C1 is a non-truth functional logic, namely, it lacks congruence for its paraconsistent negation connective with respect to the equivalence that algebraizes the classical fragment. In general, it may happen that we have that phi is equal to, or phi is equal to psi, it's true, but it will be not true that not psi will not be equal to not phi. It's very unusual property because which distorts all the congruence rules. Yes, it's not really, but later try to say exactly in what sense we need to be peaceful with such an equivalence relation. It's not in a classical sense. It's not in the classical sense an equivalence. It's not a classical congruence in the classical sense, in the sense of a mathematical sense. But in non-classical sense, it works. Sorry. Since C1 can be seen as an extension of classical propositional logic by paraconsistent negation, then the key idea will be to leave paraconsistent negation out of the chosen subsignature while still including the classical negation. The full signature represents, therefore, the algebraizable fragment of C1. So consider the subsignature gamma such that the set of operators include a classical negation and the rest is the same. Note that since paraconsistent negation is used in the definition of classical negation, the subsignature gamma is not just the reduct of the signature of all signatures sigma C1 obtained by excluding this non-classical negation. It's much more complex question. Subsignature is not just the reduct. It's procedure much more complex. Taking into account the C1 is a non-truth functional logic, then to allow for non-congruence connective for the sort phi must be a hidden sort too, so that one is forced to reason behaviorally about formulas as well. This can achieve by considering behavioral logic over an extended signature. For this purpose, given a signature sigma with a sort or types S and operation phi, one need to define an extensional sigma 0 with extended types and extended set of operators, such that as set of sorts will be extending with the help of the sort of observation formulas. The index set of operation is such that you see. It's hard to say it in words. Please look here to see, but it's nothing unusual. The only interesting is that such that as extended Holden signature obtained from sigma to sigma 0 can then be defined on sigma 0 with an extended with additional sort of observation of formulas. The choice of this sort as the name for the new sort is clear. It is intended to represent the only visible sort of the extended hidden signature. Now let K star C1 be a class of sigma 0 algebras with extended signature, and that gamma behaviorally satisfies the following set of hidden equations. You see the set of hidden equations. It's just an algebraic translation, and on the right side you see the equal to T, and gamma behaviorally satisfies the following hidden quasi-equations. Here the algebraic symbol, this wave equality, is used to avoid confusion with the usual symbol for meta-level equality. Since a K star C1 Z class satisfies quasi-equation from 1 to 4, we can define for observation such a sorts transformation, and over every member of this class of algebra, respectively, with help of the such it's very simple equations. You see, nothing extra unusual. For ease of notation, consider the following abbreviation. This operation O from constant phi will be denoted as absurd. This operation of the constant T will be denoted as T big T. For negation, we have standard definition. Why we need such a definition? Because
it's a kind of homomorphism which preserves all connections.
Yes, but all connected is a simple operation with this visible sort. Class K star is tend to be a possible algebraic counterpart of C1. Calera, Gonzalez, and Martins introduced this class of algebras over richer signatures that contained a priori the visible connective, which were introduced in the end of the list, and assumes that the visible part of every algebra is a Boolean algebra. In this class, that is in K star, is a Boolean algebra. It is interesting to know that also we define the class K star over a purist signature. One is able to define the same visible connectives as abbreviation and further prove the following result. Proposition: for every algebra from this class K star C1, we have this algebra with such signature is a Boolean algebra. That's exactly the motive for use such a symbols, because simply to define this is a Boolean algebra.
So you are making the algebra into Boolean.
Not into Boolean. On this phone, I decided as a Boolean algebra with the help of this visible source. I use this operation on visible source.
Yeah. So it's kind of invisibly Boolean, but
In
on
the-
the surface.
Yes, I think it's important. And so on. But it's only half of a story, because in the literature there are in the literature other proposals of algebraic counterparts for C1. One important example is the case of the so-called Da Costa algebra proposed by Da Costa himself. Still, the precise connection between C1 and this class of algebraic structure has never been established. Main objection is due to the fact that more than a set and operation over the set, this structure has also a relation over the set. By the Costa algebra, we mean a structure on the left corner, such that for every ABC x in S, the following conditions hold. This is axiomatics for this Da Costa algebra. My previous point was that we use special relation of less or equal, which is not order but only a priori relation.
First, 10 properties
Quasi-order, pre-order relation.
should give Hayes in algebra or not.
Which algebra?
Hayes.
In a sense, yes, because Da Costa is too late formulation. First axioms is the usual axiom from the exponential, but the other axioms are different and unusual.
The first 10,
Yes, exactly. If there exists x from S such that it is not true that x and not x is not equal to 0, the algebra A is said to be a proper Da Costa algebra. In a Boolean algebra, we always had that x and x is equal to 0. And here, not. It will be not equal to 0, because we we deal with a paraconsistent algebra. And in paraconsistent algebra, it will be the case that x and xx is true. Oh.
Boolean algebra and Python algebra should be a special case of Da Costa algebra.
It's not special, it's a hidden algebra. Hidden algebra on this background of this Da Costa algebra. And exactly the question is, what is this relation? Because behavioral algebra deals in the usual way. Moreover, it was shown by Gonsalves that for a given algebra from this class K star, for this behavioral algebra, we can obtain from it a Da Costa algebra for any such behavioral algebra, and also, given a Da Costa algebra U, we can obtain from it an algebra AU which belongs to that class K star of algebras, behavioral algebras for C1. Moreover, these constructions are inverse of each other in the sense that AUA is isomorphic to A, and moreover, UAU is isomorphic to U. So the approaches are equal in a sense. There is also even evaluation semantic for C1 introduced by Da Costa and Dawes. Evaluation for C1 is a function from the language of C1 to the set to elements sets with 0 and 1 as only elements of the set that satisfy the following conditions. You see, most interesting for us is that we have point 6 and point 7. You see, we have only in one direction. If v of xi is equal to 0, then v of non-xi is equal to 1, but not in other direction. Only in one direction. It is a source of non-truth functionality of the semantics. It's not truth functional. Nevertheless, it's evaluation semantics. If one compares both algebraic structure of Da Costa system C1 then it is obvious that we have here two different situations for one and the same logical system. And if we recall Gottlob Frege's formulation in the Foundation of Arithmetics, where he says never to ask for the meaning of a word in isolation, but only in the context of proposition, then the question arises, what is the genuine context of C1? Behavioral or another one, this original Da Costa, authentic Da Costa context?
Genuine context.
Genuine, because we have two contexts. One must be genuine. We have two different contexts. Which is genuine? One must be genuine, not both two.
But at which sense genuine?
Oh, it's a question. It is exactly the question. We need some arguments in the, for one or another approach. And we haven't such an argument. We have construction, enough argument for the help to define which is better. Trying to answer this question, it was to pay attention to such an obstacle that the Costa algebra says also the foundation of paraconsistent set theory. It is known that there is a system that F1 of paraconsistent set theory that related to Church's version of Zermelo-Fraenkel set theory that F0 with a universal set as the Costa paraconsistent first-order logic C1 with equality is related to the classical first-order predicate logic, first-order predicate calculus. In essence, the ZF1 should be partially included in ZF0, though the latter is also to be contained in a certain sense in the former. Is a quotation from the Da Costa. The basic set theoretic concepts of ZF1 are analogous to those of ZF0. Also, the concept involving negation give rise to two notions, one involving the weak negation and the other involving the strong negation, of which we spoke before. As a result, we have, for instance, two empty sets. For example, the first classical empty set, where we have x is the set of such x that x is not equal to x, and non-classical paraconsistent set, where we have the vice versa. First is paraconsistent, as the second is a classical empty set. And then we have that collection of all sets plus empty paraconsistent empty set, universe, mid join, and this classical complementation. Universe is defined as usually a set of such x that x is equal to x, and complementary is such that y of such y that y is not belongs to x. Form in ZF0 a complete Boolean algebra, and ZF1, sorry, it is exactly vice versa. First must be with a star, and the second must be without star, empty set. Collection of the set plus this operation form a paraconsistent algebra of sets. Here, this paraconsistent complementation is such the set of such one that exactly not. The idea is very simple. We have two algebras using these operators on sets. Okay. Moreover, every proper da Costa algebra has at least 3 elements instead of 2 elements for Boolean algebra. Well, it is an example of such an algebra should be described by the following tables for the operation. From the last in this list, on the bottom of this list, we will have the operation with negation. It's a source of this valuation semantics, because you see here we must pay attention to obtain it only in one direction. We have direct definition for the negation, and not in another direction. As a consequence, for da Costa algebra, the following useful property of Boolean algebra does not work. Every Boolean algebra is isomorphic to a subdirected power of 2, the 2 elements Boolean algebra. Maximally, we may have something like every da Costa algebra is isomorphic to a subdirect power of 3, the 3 elements of da Costa algebra. This should be the latent source of non-truth functionality of C1. So, for example, if we can define, usually we have how we define the set of all subsets of the set. We have 2 in the we have 2 and X. We have defined the subsets. All the parts from X. But in paraconsistent case, we have 3. In the Costa case, we will have 3 elements algebra. So we will have such subsets which really are subsets, and such subsets which maybe are subsets and maybe not are subsets. In this, according to this set theory, first trouble this way. Also, it can be reason for troubles with the congruence relation in da Costa algebra, since this relation now is in fact defined classically in non-classical context. So, for example, trying to make it more clear, I propose such a simple example with local and global ontology. For example, we have the usual picture of this, the surface of a surface, the sea, and the stratosphere. The people who lived on the surface, they have 3 levels ontology: global ontology, atmosphere in which they lived, the inhabitants of the atmosphere, and local water, and second local ontology, stratosphere. This is local ontology for those who lived on the surface. Another. For those who lived deep in the sea, they have 2 levels of ontology. Global is water, because this water is what is the environment. Local, they have 2 layers: atmosphere, stratosphere, as weak atmosphere. When they're trying to use the planes and rockets, they will deal with stratosphere and atmosphere. But for them, it's exactly another kind of.
I mean, if I'm a fish.
Yes, if I'm a fish for.
So my local is water, and my global.
No. Your global is water. You lived in here. Local because you never. Only in some cases you deal with atmosphere, stratosphere. Not every day. So for the two-letter ontology for the inhabitants of the stratosphere. Global, they have stratosphere because they live in stratosphere. Globally, they're trying to find the stratosphere everywhere. Locally, they have atmosphere, strong stratosphere, atmosphere, strong stratosphere, local stratosphere. For them, atmosphere will be simply weak, strong atmosphere, strong stratosphere, because we have too much air here, too much oxygen. And stratosphere, we have small quantity of oxygen. For them, it's exactly the question only in quantities. The situation is the same. And locally, they have water. When they're trying to find the fish. What is what is the allusion to our case? Our case is if we have globally, we work with the usual ZF0 to this Zermelo-Fraenkel set theory, then we must have locally paraconsistent set theory. But it will be, everything will be changed if we will have that paraconsistent set theory as global ontology, and classical as local. So maybe the question is the source of our misunderstanding with the case of the Da Costa algebras, because we speak of congruences in the classical sense, in the Zionistic sense, but they are defined according to the nature of Da Costa algebras in the paraconsistent set. This is the main set, not while the behavioral approach is an attempt to make it from the point of view of classical mathematics, not paraconsistent mathematics. So maybe it is these two contexts, this misunderstanding, a mix of these two contexts, is a sort of this misunderstanding when, for example, this papers on the Da Costa algebra by Cornelia de Alcantara, Gonçalves Calleiras said that it's not a real algebra for Da Costa, because a real algebra for Da Costa, a real algebraic counterpart is only behavior. What is real? What is genuine? What is the main context is the question. Maybe it seems to me that it's exactly the question of relationships of two such contexts. And of course, when we say that it's a congruences in the Costa algebra, not real congruences, then the question arises: in what sense? In the usual sense, in mathematical, Tushranisi, classical, but yes, it's not a congruence at all. But from the point of view of Da Costa mathematics, which is based on the Da Costa paraconsistent set theory, it's not the true picture, because real congruences are not such as in classical and Tushranistic theories. That's all.
Thank you.
Questions?
Questions?
I asked my question during the report.
Everything is clear.
I'm not really familiar with this kind of consistent system. Is there some kind of epistemic interpretation or application?
Of course, some epistemic interpretation concerning exactly of this of the notion of behavioral algebraism. Of course, maybe behavioral algebraization, because it's trying to find in paraconsistent sets classical and consistent sets, inconsistent sets. So maybe exactly because this is position of behavioral algebraic system is position exactly epistemic, while the Da Costa's system in his Da Costa's semantics is exactly ontological way of thinking. It seems to me that it's exactly the same way to answer the question, what is the genuine context? It's simply one context is epistemic, the second is ontology.
Maybe it's superficial, but it a bit resembles what I was having in mind in my first talk. Then I talked about kind of desired knowledge representation system where you get some, say, information, but then you want to verify it. So you call that experiment, right? So you're doing something like as an individual user that gives you, say, something about what you see, so to speak, right? And make something hidden, maybe.
It exactly concerns this, the first part when I speak on the hidden and visual data, because I mean that on the first. Oh, sorry, just a moment. From this motivation for users then behavioral, it concerns the visible data can directly access a hidden data that can access indirectly. Maybe the then they can be analyzed by many programs with visible called experiments. So these experiments, exactly maybe this visible data. The question is visible data, which data are epistemic, which are ontological, hidden or visible. Maybe some of them are ontological, have ontological status, and others have epistemic status. So if we find data in the same database, but question arises, these hidden data are really data. Their structure is really structure. It's ontological structure. And behavioral is just concerning our way to work with them. And this is epistemological status.
No, but actually what we discussed already today for Tudor's talk, I think it challenges a little bit this usual view on ontology and epistemology, right? Even almost reverse it, because if you think about, say, truth constructively, right? It's not like you have some true ontology and on the top of that you have knowledge of that.
You're right that it's reverse, because I said the point of view depends on your position. Are the ontology non-classical? Then you can find classical and non-classical, but you can find non-classical and classical also.
It's not even a question of being classical. No, in my understanding at least, it's it's really epistemological, dilemma in a sense, because in one sense there is a strong tradition, of course, in logic behind it. Frege, right? Just saying that logic is basically about truth values, so it's related to ontology first. And when you want to make something epistemological, you're doing something on the top of that, right? And different tradition that actually related to Tudor's work and Artemov, that says that basically somehow you understand truth as existence of proof, right, as probability, and then you may, for example, not to have a proof, but just an evidence that proof exists.
I understand, but my remark will be concerns the nature of an intuitionistic approach. It's not classical approach.
No, whatever it's.
And we can find classical things in intuitionistic approach.
Yeah, but then that's the choice.
It can work in the reverse way.
No, right. But then the choice is whether you build your non-classical epistemological on
yes.
or you do it the other way around. You emulate classical in your.
My point is exactly concerning emulation. In which universe we live? Because, for example, in case of paraconsistence, we can try to build paraconsistent machines when we try to obtain from the usual classical data and classical machines. We're trying to emulate, for example, this the cost of algebra on the apparatus level, and then trying to use to make such a computer, in which we also will have such data types hidden and visual. But what will be the origin of this data? It will be paraconsistent, but it was built from this usual classical things. We lived in a classical world. What will be the same? This emulation is epistemic or ontological.
Yeah. Depends on your.
Okay, it depends. There is not such a strict question that this must be so. I don't know. I'm trying simply that we have such an echo of this debate in such question concerning behavioral approach and so on. So this is interesting from the philosophical point of view.
This paper may go to our grant.
Yes, later maybe. It's not prepared. It's just on the talk. It's not the paper. Later on I'll try to do.
But you have something else. Что-то есть другое.
Конечно, я же это уже публиковал. Путос. Я же там гриф нашел. Published a paper in the framework of our grants concerning the potoses, such a paraconsistence analog of topos. The idea was of some Brazilian mathematician, Sete, seems to me, who proposed 10, maybe 20 years ago, this idea of the potos. Because we know that topos could be would be considered as universal mathematical constructions. And then he proposed that maybe we can build some categories on the pattern of topos, but paraconsistent by its nature. So I tried to do it and publish this paper in one of our grants. It will be published in Logical Investigation. Yeah. And then again the question, because we will not, in this paper, I will not speak on the Cernella Frankel or Da Costa paraconsistent, or Da Costa, only Da Costa, either in the base of the universe, only Da Costa system. And only potos from the very beginning is construction, is a paraconsistent construction. We find in institutionalistic and classical, you will see that our axioms contains some institutionalistic axioms, so we traditional also, but it's exactly it's another level. It's not basic level. While in topos we have institutionalistic construction as a basic level. The basic. So the universe of topos is institutionalistic one. It will be paraconsistent. But the question is exactly in this dilemma, in which world we live. Paraconsistent, if we will have such a possibility to develop paraconsistent mathematics in potoses. But we can also develop paraconsistent mathematics in toposes too. The same question. What maybe simply this is not the decision, but simply the answer that in one case it will be epistemic origin, this ontological origin, and so will be simply such a classification in both cases. Paraconsistent will be in potoses. It's an ontological question of this origin of and in toposes is institutionalistic. It's also ontological, but it's an ontological question. They change this, its nature. This is idea.
Okay, thank you. Okay, thank everybody. I think we may take some beer. Yeah? Ну, есть время?
Да, есть.
Okay, I just need some time to close the room and. Да, чуть-чуть прибраться. Сейчас.
Что за стол?